Okay, so this is the third video for section 8.1. So let's do another example. So let's expand the following products. Expand the following complex products. Okay, so number one, let's say I have quantity 2 plus 3i times the quantity 4 minus 5i. So remember, this is like the z and the w we had before. So 2 plus 3i times the quantity 4 minus 5i. What I'm going to do is I'm going to consider them vertically. So 2 plus 3i, I'll call that my z. And my w, I will call 4 minus 5i. So when I take the product of z times w, what I get should be, in orange, 8 minus negative 15 for the real part, and negative 10 plus 12 for the imaginary part. So 8 plus 15, so that's going to be 23, plus 12 minus 10 will be 2i. Okay, so let's see, 23 plus 2i. Now that is a real, sorry, not a real, a complex number. So before we had the difference of squares, which resulted in the sum of squares, which gave us a real number. But since these are not complex conjugates, they produce a complex number when multiplied. Let me move this over a bit. Okay, so number 2. What do we have? Let's say we have quantity 3 plus I squared. Okay, so once again, I'm going to let z be 3 plus 1 times I, and I'm going to let w be 3 plus 1 times I. Now these are not conjugates, so they will not produce a real number. They should produce a complex number. So z times w will be equal to the real part, which is, oh, no, it's not. It's 9 minus 1, to which I'm adding the imaginary part, which is going to be 3 plus 3 times I. Okay, so we have 9 minus 1 is 8 for the real part. And then we have, what do we have for the imaginary part? 3 plus 3 is 6. So there we are. Okay, so number 3, I kind of prefer this method to foiling, but it's up to you. So let's say we have 1 minus 5 times I times the quantity 2 plus 7 times I. So once again, I'll call this my z. So my z is 1 minus 5 times I, and my w will be 2 plus 7 times I. So therefore my product, z times w, will be equal to orange for the real guys. So 2 minus negative 35, to which I'm adding the imaginary part, which should be 7 plus 10. times I. Okay, so what does this give us? This gives us 2 plus 35 is 37, plus we have 7 plus 10 will be 17 times I. Notice this once again is a complex number. Okay, so hopefully that makes sense. Okay, so now another example. Let's use the conjugate to rationalize the following. So example, use the complex conjugate, rather. The complex conjugate. Conjugate to rationalize the following. So number one, let's say we have 3 divided by the square root of negative 36. Okay, so we have 3 divided by the square root of negative 36. So I claim that that's 3 over 6i, because the square root of 36 is 6, and the square root of negative 1 is I. So in order to rationalize this, I need to, actually let me put this in purple. I need to find the complex conjugate of purple. So in this case, do you agree that that's 0 plus 6i? So the complex conjugate will be 0 minus 6i. So, and this is because we had z equals to 0 plus 6i, meaning the real part didn't exist. So z bar will be 0 minus 6i. The complex conjugate, notice, oh shoot, I forgot to put that there. Notice that the it's the complex part that's always negative, not the real part. Okay, so what do we have here? 3 times negative 6i should be negative 18i. And in the denominator, we'll get a negative 36 times I squared. But of course, I squared is negative 1. So we get a negative 36 times a negative 1. And by the way, we can reduce some of these negatives here. This negative here, and also 18 goes into 36 twice. So this becomes what? This becomes the negative I over 2, actually. So there we are. Interesting. Okay, so let's do another one. Number 2. Do I have enough room? Let's see. Let's say we have 5 over 3 plus 4i. Okay, so I'm given 5 over, let's call my z in this case 3 plus 4i. So what I would need to do is multiply top and bottom by the conjugate, the complex conjugate, 3 minus 4i. So it's always the complex part of the imaginary number, or the complex number, that becomes negative. Okay, so what do we get here? Distributing in the numerator, 5 times 3 is 15, and 5 times 4, or negative 4, is negative 20i, divided by what amounts to the difference of squares in the denominator. That is 3 squared minus 4 squared I squared, 4 squared I squared. But remember, I squared is negative 1, so we should always get the sum of squares. So in the numerator, we have 15 minus 20i, and in the denominator, we have 9 plus 16. Okay, so what does that give us? That gives us 15 minus 20i divided by 9 plus 16 is 25. This does reduce if we care. 5 goes into everything, so 5 goes into, Let's see if I can move this over a little bit to the left so I can keep it on this page. So 5 goes into 15 3 times, into 20 4 times, and into 25 5 times. So this becomes 3 minus 4i all over 5. Okay, another example, part 3. Let's say we have 3 minus 2i divided by 3 plus 2i. Okay, so we have 3 minus 2i divided by 3 plus 2i. So to rationalize, we multiply top and bottom by the conjugate of the denominator, which is 3 minus 2i. 3 minus 2i. So notice in the numerator we have a perfect square. So in the numerator, the perfect square will be first guy squared minus twice the product of the first and the second plus the second guy squared all over what amounts to the sum of squares, 3 squared plus 2 squared. Hopefully I can skip the negative i's or the I squared at this point. Everyone knows that this factors as a sum of squares now in the denominator. Okay, so what do I have? In the numerator, I have 9 minus 12i plus 4i squared all over 9 plus 4 . So what this gives me then, in the numerator, I'm going to replace the I squared with a negative 1. So this becomes now, let me just go ahead and write it, a negative 4. And this is because I squared is negative 1. All over 13. But I can subtract 4 from the 9. So 9 minus 4 is 5. So 5 minus 12i all over 13. And there we are. 13. Okay. Okay, so let's note. This is kind of a different subtopic now, so note. So the graph of a function, or if the graph of a function rather. So if the graph of a function, if the graph of a polynomial function has more turning points, than x-intercepts, then some of its roots are complex. Okay, so what do I mean by this? So let's consider, let's say, got x and y coordinate axes. So let's say I have a nice, sinuous, lovely polynomial function, which is so nice. Polynomial functions are lovely. Oops, well, okay, I'm trying to make them lovely. Yeah, polynomial functions are nice, sinuous, lovely graphs. Okay, so notice, how many turning points do I have here? So turning points. So if I'm going up and then I turn back around, this is 1. Going down, then I turn back around, 2. Going up, then I turn back around, 3. Going down, then I turn back around, 4. So x-intercepts, actually maybe I should do that in hot pink. So x-intercepts let's see, 1, 2, 3, 3. So note that four minus 3 is equal to 1. So that is, i.e., more turning points. More turning points. Doesn't matter how many more. It just has to be at least one more. So more turning points than x-intercepts. Than x-intercepts. Therefore, complex roots. Therefore, has complex roots. The graph of this function, whatever polynomial